All right, in the last video, I said some limits are going to require some new techniques. In the last video, I said we're going to be able to use derivatives to help us evaluate some limits. This is the video where I'm going to show you how. I want to start with a quick note that the spelling of this person's name, and there is a long, actually, no history lesson today, but L'Hopital's rule was actually not discovered by L'Hopital, but anyway, you may also see it written like this. If you want to write it without a circumflex, and that's usually what it's called, how it's spelled. This is the hat is apparently called a circumflex. I didn't know that. But yeah, that's pretty much it. So let's just jump into the theorem, and then we'll talk a little bit about how it works, how to use it, and we'll go on. So this is L'Hopital's rule. The moment you've all been waiting for. The last theorem of this class. And it says, like many of our other theorems, suppose that f and g are differentiable on some interval I. Specifically an open interval I. Containing some point A. But then they don't actually have to be differentiable at A. So again, this is just a very common thing, saying we don't need these functions to be differentiable everywhere. If we're looking at limits, we don't even need the functions to be differentiable at the point. We just need these functions to be differentiable near the point. That's all this means. Let's have these two functions differentiable around some point. Again, that point A is going to be where we're looking at for our limit. Okay. So let's see, suppose this, and then we're going to have one of the two indeterminate forms. So either these limits are both going to be 0. The limit as x approaches a of the function f is the same as the limit as x approaches a of the function g, and they're both 0. Or maybe they're both infinity. Okay. So we're having one of these indeterminate forms. Either both of these functions go to 0, we have 0 over 0 in that case, or both of these functions go to infinity, plus or minus infinity, and then we'll have the infinity over infinity case. Then L'Hopital's rule tells us that the limit as x approaches a of f of x over g of x, again, this is an indeterminate form situation because the limit of this, we can't use limit laws. We have 0 over 0. Limit laws only apply when the denominator is not equal to 0. Is the 0 over 0 indeterminate form, or the infinity over infinity indeterminate form. And L'Hopital's rule says that this limit is the same as this limit. Whoa. Is the same as the limit of these functions of their derivative. The limit of their derivatives. And you might say, Jason, doesn't that just make it worse, not better? The derivative is sometimes messier. Well, sometimes, but this is actually really powerful. The limit of a quotient of functions is the same as the limit of their derivatives? Huh. Okay. So again, this is, small thing we have to do, the fine print, if you will, assuming the right-hand side exists or is positive or negative infinity. And this works as x if a is infinity as well. Okay. So maybe a small side note also works if a is plus or minus infinity, or we have one-sided limits. Oh no, I'm writing behind my head again. So that's the theorem. We're going to use the theorem in the next, there's too much writing. One-sided limits, plus or minus infinity. That's what's back there. Let's use this and make this a little bit more clear. Let's clarify what's going on. A lot of introductory stuff in this section. let's get our hands dirty. So example 1, evaluate the following limits. Part A, the limit as x approaches 0 of 1 minus cosine of x over x. So this isn't a rational function. Rational function is a polynomial divided by a polynomial, and we have a trig function on the top. But trig functions are continuous. Trig functions are continuous. The denominator is just x, that's continuous. This is just the composition of functions, or the product of functions, or the quotient of functions. Any kind of limit law you want to use says that we can just evaluate the top and the bottom separately using direct substitution, and that's the limit, because they're both continuous as long as the denominator is not equal to 0. But of course, the problem here is if we try direct substitution, we get 1 minus the cosine of 0 over 0. Dividing by 0 is already a problem, but even worse, the cosine of 0 is 1. This is the 0 over 0 indeterminate form. Can we use L'Hopital's rule? Suppose the top and the bottom are differentiable on some small interval. Well, the top and the bottom are differentiable everywhere. 1 minus cosine of x, differentiable everywhere. X, differentiable everywhere, so we've got that. Are the limits both 0 or the limits both positive or negative infinity? Yep. Limit of the top is 0, limit on the bottom 0. Great. Then we can use L'Hopital's rule, assuming the right-hand side exists. So L'Hopital's rule. So a lot of times what we'll do is we'll write an equals sign with LH on top. This is not necessary, but it's very helpful to show that we are indeed using L'Hopital's rule. So this is going to be the same as the limit of their derivatives. Well, the derivative of the bottom is 1, and the derivative of the top is positive sine of x. Derivative of negative cosine is positive sine. Notice that we're not taking the derivative of the whole thing. The derivative of the whole thing would require the quotient rule. All we're doing is using L'Hopital's rule, saying that this limit, if we have an indeterminate form, this limit of that quotient is just the limit of the derivatives of each. So don't confuse it with the quotient rule. We're using a different theorem here. We're not just taking the derivative of the whole function. We're using this specific rule. And now you can immediately see that we don't have this indeterminate form anymore. Right? The bottom is 1. What's the top? Well, again, let's try to use direct substitution since the top and the bottom are both continuous. If we use direct substitution here, we get 0 over 1, which is perfectly fine. This limit should equal 0. Let's look at that. Let's graph it. Let's see how it looks. The top function is 1 minus cosine of x, and the bottom function is x. And as x approaches 0, we say this function approaches 0. Good. You can see it right here. As x approaches 0, the function approaches this hole. What's the function value at that hole? Well, the function doesn't exist, but if it did, it would be 0. The limit of the function. As the x coordinate gets close to 0, the y coordinates are getting close to 0 as well. Let's get some more practice. Part B, the limit as x approaches 1 of the sine of pi x over the natural log of x. And again, both the top and the bottom functions are continuous on their domains. So as long as we're not dividing by 0, then we can use direct substitution. So the sine of pi times 1 divided by the natural log of 1. Well, natural log of 1 is 0. Sine of pi is the y coordinate at pi radians. The y coordinate at pi radians is y coordinate at 180 degrees on the unit circle. It's also 0. 0 over 0 indeterminate form. So we have two differentiable functions. Two differentiable functions. And their limits are both equal to 0. So the limit of their quotient is the limit of the quotient of the derivatives. We can use L'Hopital's rule again. This, by L'Hopital's rule, is equal to the limit, as x approaches 1, of the derivative of the top divided by the derivative of the bottom. Derivative of the top, well, the derivative of sine is cosine. But we only know the cosine of x. We only know the derivative of the sine of x. There's no property that we have for the derivative of sine of pi x. So we have to use the chain rule because the inside is not just x. So we have to multiply by the derivative of that inside function, which is just pi. The derivative of the natural log of x is 1 over x. And now you can either try to simplify this or use direct substitution. Again, the top and the bottom are continuous everywhere on their domains. So if we use direct substitution, we're going to get the cosine of pi times 1 times pi divided, divided by 1 over 1. I tried to breathe saliva. Bad call. Don't do it. If you learn nothing else in the video, learn not to drink or breathe saliva. So the cosine of pi, that's the x-coordinate at pi radians. What's the x-coordinate on the unit circle here? -1. Unit circle is a circle of radius 1. So this is the point. -1, 0. So we get -1 times pi. 1 divided by 1 is still 1. We get that this limit is -pi. Let's see this graphically. The sine of pi x over the natural log of x. As x approaches 1, what are we getting close to? Well, we're getting really close to about -3.1. Oh, that's kind of close to pi, isn't it? -pi. The y value is getting really close to -pi here. And in fact, if you graphed -pi, that's not -pi. If you graph -pi, you would see that, hold on. All right, you would see that it is exactly at this location there. But this function, the blue graph, is not defined here. It kind of backfired on me a little bit. Yeah, you can see it is indeed at -pi exactly. The limit of this function, as x gets really close to 1, again, the function's not defined at 1. That causes us to divide by 0. But as x gets really close to 1, the function value gets really close to -pi. Remember your limits. Both calculus limits and limits in real life. The limit as x goes to infinity of 3x plus 5 over 2x plus 1. Let's look at a different indeterminate form. Like sometimes, we haven't done this too much, but sometimes you can think about plugging in infinity. Like if we use direct substitution here, infinity is not a number, but right, we're going to have 3 times infinity plus 5 over 2 times infinity plus 1. Well, 3 times an infinitely big number is infinitely big. Add 5, still infinitely big. Multiply an infinitely big number by 2 is the same thing. This is the other indeterminate form that we've talked about. Infinity over infinity. And again, this is an example of a rational function, a polynomial over polynomial, that we have tools of finding this end behavior. But instead of remembering all those tools, let's just use L'Hopital's rule. L'Hopital's rule says this is the same as the limit as x goes to infinity of the derivative of the top divided by the derivative of the bottom. That's quick. The end behavior as x goes to infinity, as x goes all the way to the right, should just be 3/2. Let's see if it's true. Let's see if I'm lying to you. 3x plus 5 divided by 2x plus 1 As x goes really far to the right, what's happening to the y values? Well, let's zoom out a ton. What's happening to the y values? Kind of getting close to 1.5, 1.5, 3/2. Okay. That's L'Hopital's rule. Now you have the tools to do the L'Hopital's rules problems for the nice indeterminate forms. But I have another video coming up with more of these examples. So the next video is just more examples, nothing new. And then we'll bring in some new stuff after that. Good luck.